Sí.
Listo.
Ahí, le doy admisión a Gianmassimo o tú, Juan.
Yo,
Ok.
no,
Ya.
ok, ya
Sí,
está.
sí. Está ahí en el waiting room. Sí.
Listo, ya tienen los permisos.
Hola, hola a todos. Hola, Oscar.
Hola, Gianmassimo, ¿cómo estás?
Hola, Gianmassimo, ¿qué tal?
Hola. ¿Todo bien? ¿Ustedes? ¿Todo bien?
Todo bien, todo bien. Ya ya resguardados,
Ah, sí,
pero bien.
Todos en modo navideño.
Sí.
¿Y allá, cómo está ya el asunto?
Ahora estoy en Italia. Sí, bien. Bueno, cerrado en la casa, pero sobrevivo. Sí. ¿Y ustedes también cerraron? Ah, no. ¿Están en la oficina ustedes?
No, yo estoy en casa.
Yo también en casa.
Ah, bien. Sí, veo el árbol ahora, sí. Bueno, ¿y cómo hacemos? ¿Quieren probar para ver si se ven las
Sí, por favor.
transparencias? Espera un segundo. Voy a ver. Soy share screen ahora. Encontré. Perfecto. Creo que ven. Pueden ver, ¿verdad?
Sí, sí.
Ah,
Sí,
perfecto.
perfecto.
Muy bien. Entonces la voy a hacer en inglés, pero porque no sé muchos de los términos.
Sí. Yo, de todas maneras, cualquier pregunta que te hagan en español la
Sí.
entiendes, ¿verdad?
Sí, es perfecto. Y ustedes ya terminaron las clases, espero.
No.
¿No? ¿Siguen?
Bueno, ya no más exámenes.
Estamos en época de exámenes. Yo justo terminé ayer
De hacer exámenes.
de hacer exámenes, sí. Complicado, ¿no? Pero ya.
Bueno,
Él todavía no termina.
bueno.
¿Tú?
No, este semestre yo lo tuve de vacaciones. Tengo
Oh,
tres cursos empezando en enero.
3 cursos.
Sí, los puse todo en un semestre para ver cómo funciona. Y no sé si es bien. Vamos a ver el próximo. Seguro el próximo semestre sí va a ser muy, muy duro. Pero bueno.
Bueno, algo así me pasó a mí este semestre. Agarré más de los que debí. O sea, el semestre pasado por lo de la pandemia le dije a los alumnos, no, miren, si lo dan de baja, yo les ofrezco el curso para que no se atrasen, ¿no?
Sí.
Y al final fueron 3 frente a computadora bastante pesados que...
Sí.
el otro semestre nomás uno, porque...
Sí, también se te cansan los ojos, es terrible, sí, al final del día.
Digo, pues ni modo, ¿no? A veces pienso que será mejor grabar la clase y nomás se las dejo ahí en la página y que la oigan y luego ya
Pero no, bueno, yo sí, tenemos que hacer cosas así, pero no es muy lindo. Es como ver en YouTube, entonces le digo, mírate las lectures en Harvard, es mucho mejor. Bueno. Y también los estudiantes, sí. No pueden poner mucha atención.
Sí, para mí eso ha sido el mayor reto, porque cuando está uno trabajando con los colegas, pues están conectados porque quieren estar conectados, bueno, eso espero que quieren estar conectados y uno discute y lo que sea, ¿no? Pero cuando es la clase, me he dado cuenta que, bueno, no es mi sentimiento, que a muchos no están muy interesados y entonces se conectan.
Sí, hacen otras cosas. Sí, todo el mundo es un problema muy global esto.
Pero pues bueno, así hay que ir aprendiendo, ¿no?
Sí, quién sabe cuánto va. ¿Y cuándo empieza la vacuna en México? Porque ahora aquí se dice, en unos meses empezamos.
Aquí, creo que el veintitantos, ¿no, Oscar?
Sí, aquí se supone que ya el 18, el veintitantos, empiezan a vacunar a personal médico.
Sí.
Y a partir de enero, no, a partir de febrero, a mayores de 60, mayores de 70, por ahí.
Sí.
Y así va por etapas, ¿no? Entonces, a nosotros nos toca por allá de mayo,
Sí,
y ya los jóvenes ya les tocó hasta el otro año.
creo que sí. Bueno, no tienen problemas. Igualísimo aquí en Europa, sí. Igualísimo. Empezamos en Navidad y después se va. Hay una cola muy larga que llega, quién sabe cuándo. Pero estoy segurísimo que vamos a tener muchos problemas de distribución, etc. También por la temperatura, que es menos 70, menos 80, va a ser un lío.
Ahora, esa es con esta Pfizer, ¿no? Si
Sí.
es otra, parece que puede ser temperaturas más altas, ¿no?
El Moderna, sí. Pero todavía están haciendo los test de esto. Bueno, ¿qué? Esperamos un poquito, ¿verdad? ¿Cuánto tengo? Yo tengo 90 y pico slides, pero creo que en 50 minutos puedo hacerlo.
Yo
No
creo
sé.
que está bien 50 minutos. Digo, está programado para hasta las 11.
Sí.
No creo que sea probable a veces agarrar un poquito más de tiempo, no creo que sea un problema.
Entonces, si les parece bien, vamos a comenzar en lo que empiezo a presentar a Gianmassimo. Muy bien, entonces comenzamos. Son las 10 de la mañana. Bienvenidos a las posadas cuánticas o posadas de gravedad cuántica, en lo que esperamos sea la primera versión y ojalá sea un evento que les guste, que les atrape y que podamos seguir haciendo en otros años. Ya veremos cómo avanza durante estos 3 días. Entonces, bienvenidos a todos. Es un placer estar con todos ustedes. Es un placer haber organizado este evento junto con Ana Cabo y Miguel Sabido. Yo soy Oscar Loaiza. Les agradecemos mucho a toda su presencia, sobre todo a los ponentes que nos van a platicar sobre aspectos de gravedad cuántica en sus diferentes líneas de investigación. Entonces, el objetivo de este evento, a grandes rasgos, es precisamente ese, traerles a toda la comunidad de estudiantes y de investigadores que estén interesados en aspectos de gravedad cuántica, a investigadores trabajando en diferentes áreas y que ustedes puedan ver que realmente esta idea de gravedad cuántica pues ya tiene muchas repercusiones en la investigación de cada día, ¿no? Entonces tenemos investigadores internacionales, tenemos nacionales en diferentes áreas como la teoría de campos, física matemática, teoría de cuerdas, cosmología, gravedad modificada. Otra de las intenciones de este evento es también que ustedes conozcan el trabajo de investigación que están haciendo nuestros jóvenes investigadores, en particular algunos de nuestros grandes talentos que han egresado de la Universidad de Guanajuato. Además, por supuesto, de los expertos panelistas que hemos invitado, ¿no? Es para mí un gran placer tener e inaugurar este evento con una plática de Gianmassimo Tasinato, un investigador de amplio reconocimiento internacional. Déjenme decirles en palabras muy breves su trayectoria, que es extensa y por supuesto me voy a quedar corto al mencionarla, pero Gianmassimo hizo su doctorado en Italia, en Sisa, Trieste. Posteriormente hizo una serie de postdocs en diversas áreas de Europa para terminar ahora trabajando como planta, como investigador ya contratado en la Universidad de Swansea, en Reino Unido. Ha publicado más de 100 artículos, tiene un número de citas considerable, más de 4,000, 5,000 por ahí. Es un experto en diversas áreas, en particular en cosmología y en los aspectos cuánticos de la gravedad que influyen en las etapas iniciales del universo. Y hoy nos va a platicar sobre pruebas sobre el universo temprano a través de ondas gravitacionales. Gianmassimo, es un placer tenerte con nosotros. Déjenme decirles ahora un poquito la dinámica de las pláticas. Gianmassimo entiende perfectamente el español, el castellano. Sin embargo, va a hablarnos en inglés. En física así pasa. Entonces nos va a dar la plática en inglés. Pero sus preguntas son bienvenidas en castellano. Él las entiende, las puede responder. No hay ningún problema con eso. Entonces yo les pido que en caso de que tengan preguntas muy urgentes, las hagan durante la plática. Si no, esperamos al final de la misma. Vamos a tener alrededor de 50 minutos para la plática, 10 minutos para preguntas. Y el método para hacer la pregunta es levantar su mano en su pantalla de Zoom. Por ahí tienen la opción de levantar la mano o mandar su pregunta por chat y les abriremos el micrófono a los que consideremos tengan el acceso al final de la plática o durante la plática si es muy necesario, ¿sí? Entonces, Gianmassimo, bienvenido. Muchas gracias por haber aceptado la invitación y comenzamos. Adelante.
Perfecto, muchas gracias, Oscar. Sí, es un placer estar con ustedes. Y bueno, voy a dar la plática en inglés entonces. Now, I hope you can see my screen as a full screen. If not, please let me know and I can change the size of it. So today I'm going to tell you about how to use gravitational waves, the new physics that opened up few years ago on gravitational waves to probe aspects of cosmology in the early and late universe. So what we all know so far is that what we all heard is that gravitational waves are a very, very important tool to understand the physics of black holes. We have seen many observations so far from ground-based detectors like by LIGO-Virgo collaboration, gravitational waves from merging black holes. What today I want to tell you is about a possible future additional opportunities that the physics of gravitational waves can provide us about studying the early universe cosmology, focusing on cosmological inflation, and theories of dark energy, of late universe cosmology, because gravitational waves that travel through space-time can collect small but maybe seizable information about the expansion of our universe and the theories of dark energy. So these are the two topics that I would like to briefly review for you today. And I will I start with the early universe, then in the second part, dark energy and theories of gravity. The common feature is physics of gravitational waves. So let's start with the early universe and with cosmological inflation, and I will try to explain to you why gravitational waves can be a very important and interesting way to probe our knowledge of the early universe and of cosmological inflation. So first of all, what is inflation? Cosmological inflation is a short period of superluminal accelerated expansion that we believe it occurred within the first seconds of our universe life. It was proposed, this theory, in the early 80s to solve some of the basic problems of standard Big Bang cosmology, that is the horizon flatness and the entropy problems. But afterwards, it has been realized that this theory automatically encodes an elegant mechanism for generating the initial conditions for our universe, in particular for providing the primordial seeds for the cosmological microwave background radiation and for the large-scale structure of our universe. The mechanism of inflation has been so far well tested, at least for some of the predictions. So what is this mechanism? This mechanism puts together the physics of quantum mechanisms with cosmology, with curved spacetimes. The idea is that cosmological fluctuations are produced by quantum effects at very short distances in the early universe. Then inflation starts to expand very, very rapidly, almost exponentially during inflation. And these quantum fluctuations, the wavelengths of these quantum fluctuations become very large, of the size of our universe. They actually cross the horizon, the cosmological horizon. They become classical, And only after inflation ends, so inflation lasts a very short time, and only after inflation ends, during the normal expansion phase of our universe, then these fluctuations that were produced during inflation, they re-enter the horizon, they provide the seed for the formation of structure of the universe that we observe today. Okay, so how to describe these concretely, the predictions of inflation? During inflation, the fluctuations of the metric can be decomposed in scalar, vector, and tensor. Scalar fluctuations are the main sources for the fluctuations in the temperature fluctuations of the cosmological microwave background radiation, that those predictions have been well tested by CMB experiments. Tensor fluctuations that are gravitational waves instead could be revealed, hopefully, by studying the polarizations of the CMB. So what are the predictions of inflation for what respect these tensor fluctuations? The predictions of inflation is that they should exist as stochastic background of gravitational waves. Gravitational waves that come from the early universe, from inflation, that come from every directions. And this is a prediction of inflation. In the simplest model of inflation, these gravitational waves are just spin-2 modes that are free and that travel in a curved background, in a Friedmann-Robinson-Walker background with scale factor A. It is relatively simple using basic quantum mechanics to calculate the amplitude of these fluctuations, and that is encoded in a quantity that is called power spectrum. It's just a 2-point function. And this power spectrum results to be proportional to the Hubble parameter h during inflation. Starting from the power spectrum in tensor modes in gravitational waves, it is possible to compute what is called tensor to scalar ratio, the ratio between the spectrum of gravitational wave over the spectrum in the scalar modes that influence the temperature fluctuations. And this is calculable in the simplest models of inflation, depends on a slow roll parameter epsilon that tells us a lot about the energy scale of inflation and the size of the inflaton field excursion. So while we have observed the spectrum of scalar fluctuations and the temperature fluctuations of the CMB, we did not so far observe gravitational waves from inflation. We have seen gravitational waves from matching black holes, but not these early universe gravitational waves. We have only an upper bound on the size of this tensor to scalar ratio that is of order 10 to the minus 2. The simplest models of inflation, like the Starobinsky model, predict a value for R that is of order 10 to the minus 3. So we are almost there. The sensitivity of the instruments are almost there, at least to test the simplest models of inflation. So let me emphasize, what we are talking about are not gravitational waves that come from astrophysical objects. These are gravitational waves that come from the early universe, from everywhere. These are really a stochastic background. And most of the experiments focus on trying to study the polarizations, not the temperature fluctuations, but the polarizations of the CMB. Because in the polarizations, there can be some hints for these primordial gravitational waves. Now, the question that I would like to cover in the first part of the talk is what happens. Let's suppose that this tensor to scalar ratio is much smaller than 10 to the minus 3. That is, the size of this, of the amplitude of these primordial gravitational waves is very small. After all, there are models of inflation that can predict also an R that is much smaller than 10 to the minus 3. Should we give up any attempt to probe the inflationary gravitational waves, the inflationary tensor modes? So what I would like to tell you about is the possibility of directly detect gravitational waves that come from inflation using gravitational wave experiments. So all of you heard about ground-based gravitational wave experiments like LIGO in US or Virgo in Italy. But in the future, there will be also space-based gravitational wave experiments, LISA, and we'll talk primarily about this possibility. And there are currently also experiments that use pulsar timing arrays, that use the light that comes from distant pulsars. And then the hope is that with this kind of experiments, we will be able to directly probe stochastic background gravitational waves that come from the early universe. As we probe temperature fluctuations on the CMB, we can probe the background and its anisotropies of the gravitational waves. Now, okay, that sounds very interesting, but there are theoretical, let us say, theoretical problems. Okay, the first problem is that in the simplest models of inflation, the amplitude of the spectrum of gravitational waves is nearly scale invariant, and it is almost flat in frequency. So let's give a look to this plot. This plot, in the x-axis, there is the frequency of the gravitational waves. In the y-axis, there is a quantity, this is omega GW, that is proportional to the spectrum, to the amplitude of the gravitational waves. So there is frequency and amplitude. In inflation, the amplitude is very small. In these units, it is of order 10 to the minus 14. So these are sensitivity curves of some of the experiments that I mentioned to you before. So for example, this is sensitivity curve for space-based interferometer like LISA. So all this means that all signals that are inside this region can be detected by LISA. Signals that are outside this region cannot be detected. So you see that in inflation, the predictions is that the amplitude is much smaller than the sensitivity curves of LISA. This is, however, true only for the simplest models of inflation. There can be very well motivated models of inflation by coupling the inflaton field with other fields, we will see in a second, that enhance, that amplify the spectrum of fluctuations at the scales of interferometers like LISA, and then it could be detected directly by interferometers. So what I would like to tell you is then some of the possible ways to do so. So the idea will be to consider, instead of vanilla models where during inflation we have just a slow roll evolution, we could have a more sophisticated setup that are theoretically well motivated. For example, during inflation, the scalar field that drives inflation interact with additional fields, gauge fields, other stuff. Or one can have symmetry breaking, specific symmetry breaking patterns or non-attractor phases. There are a lot of possibilities that could enhance the spectrum, could enhance the size of gravitational waves of tensor modes at the scales of interferometers. Okay, so the idea then is to use gravitational wave experiments, ground-based, LISA, or pulsar timing arrays to probe physics of inflation in frequency scales or at energies that cannot be probed by the cosmological microwave background radiation. So the important thing is that these are a collection of sensitivity curves for different experiments. Here there is LISA, here there are the ground-based experiments, here are the pulsar timing arrays. So all these experiments will take place in the future. What I would like to try to explore and to understand and to tell you is whether we can use these experiments that will be built in order to probe the physics of the early universe. So this is the setup. So please interrupt me and let me know if you have any question as I go on. I start with a brief theory path to motivate more concretely the kind of models that I have in mind, and then with a little phenomenology with case studies to show you how the interferometer LISA will be able to probe the theoretical ideas that I tell you. So LISA has sensitivity curves that are picked at certain frequencies, and they can probe omega GW at amplitude of order 10 to the minus 3. So this kind of region. So theoretically, how can we enhance the spectrum of gravitational waves that come from inflation? So here in the box, there is the evolution equation for a spin 2 mode for a gravitational wave that propagate in an expanding space-time. So here you see there is a usual friction term due to expansion, and then second derivative along time. And here in Fourier space, I have k over h squared. So how can I change the physics, the basics physics of the gravitational wave propagation? So one possibility is to include a source term. So some source that enhance, that amplify the spectrum of tensor fluctuations. Or one changes the potential. For example, one gives a mass to the graviton. This can be well motivated in some models of the early universe. Giving the mass to the graviton, as I will show to you, enhance the spectrum at the scales of interferometers. Other possibilities that I don't have time to review here is to change the kinetic term. There are various ways to amplify the spectrum of tensor modes. More concretely, the first possibility was to give a source to the gravitational waves. So here is the equation giving a source. How can we give a source? Okay, there are many possibilities. One is, for example, to couple the scalar field that drives inflation, for example, if the inflaton is an axion field, to gauge fields. In this case, there is a transient instability of vector modes associated with this coupling that feed tensor modes and produce a sort of anisotropic stress that enhance the spectrum of fluctuations. Here in this plot, here are the sensitivity curves of LISA. We studied in a paper this model, and we shown then that the prediction of inflation, this is the prediction of the spectrum of tensor fluctuations from inflation, and here you see that it crosses the sensitivity curves of LISA. So LISA in the future will be able to probe this scenario. This scenario is also interesting because it has distinctive features like a chiral spectrum. There is parity violation in this model. So gravitational waves come with two polarizations, for example, plus and cross. And these two polarizations have different size, different amplitude in this model. So if we are able to probe this phenomenon of parity violation, then we can additionally test this scenario. Another way to enhance the spectrum of fluctuations is to produce an anisotropic spectrum at second order starting from scalar fluctuations. And there is a well-motivated scenario to do so that is associated with the production of primordial black holes. So maybe you have seen in the archive, or maybe you worked also on the idea that some of the dark matter that constitute our universe can be made, at least some of dark matter can be made of primordial black holes. It's not a particle, but it's made of primordial black holes. Also, some of the events that have been detected by LIGO Virgo could be black holes that are not astrophysically produced, but produced in the early universe by the mechanism of inflation. So how is it possible to do so? It is possible by enhancing the spectrum of scalar fluctuations at some scales during inflation. If the spectrum of scalar fluctuations overcomes a certain threshold, then primordial black holes can be produced after inflation ends during radiation or matter domination. So why do I tell you so? this thing because the spectrum of scalar fluctuations that produce primordial black holes at second order, they also enhance the spectrum of tensor modes. Because tensor modes at second order in perturbations, the scalar modes that are enhanced in order to produce primordial black holes, also they enhance tensor modes. And so they can enhance the spectrum of tensor modes at the frequency scales of LISA. So here in the left, there is a plot that shows, that discusses a scenario that produces primordial black holes of certain masses. And as an echo, at second orders, this massive production of primordial black holes, they lead at second order to tensor modes that can be probed with LISA. So you see there is a nice connection between dark matter and gravitational waves from inflation and interferometers. So the spectrum of tensor modes produced during inflation, it has a certain slope. It depends on the frequency in a very specific way that could be testable with interferometers. And I will show to you later this.
Sorry, I have a brief question. Just
yes,
can
yes.
you tell us a little bit about the difference between first order and second order corrections?
Yes. So here you see. So I don't know how much you know about cosmological perturbation theory, but maybe you heard that around a Friedmann-Walker isotropic background, at linear order, tensor, scalar, and vector modes propagate as independent fields. So tensor modes are not coupled to scalar modes or to vector modes at linear order around a Friedmann-Walker isotropic background.
Thanks.
This is not true if you go at higher orders. So at higher orders, if the fluctuations are very small, at higher orders, so this is the end of the story. But if the suppose that the scalar fluctuations are enhanced, like in these scenarios, are enhanced in order to produce these primordial black holes. Then these scalar fluctuations are no more small. Their size is very, very big, at least at certain scales. And then at second order, one writes all the equations of evolution of fluctuations, and one realizes that at second orders, there can be contributions to the evolution of gravitational waves, to the evolution of primordial tensor modes. These groups studied this effect, and they wrote the general equations valid up to second order. And for models that produce these primordial black holes, these second order corrections are not small, are actually very big, and they enhance the spectrum fluctuations at the scales of LISA interferometer. With a specific slope, with a specific dependence on frequency, that might be detectable. And I will show to you later. But this is the theory. Is it clear? I hope it is clear.
Yes, very clear. Thanks.
Okay, no problem. So I continue. So there are many other predictions that I don't enter into details, but theoretically, theoretical cosmologists just shown that besides producing this kind of spectrum of fluctuations, the stochastic gravitational wave of tensor modes is also anisotropic. They have anisotropies, and it's also non-Gaussian. So there is a huge machinery that one can very well develop machinery, and so people studied all the predictions, theoretical predictions. The question then is to probe with experiments. I will show you later. So let me continue very, very briefly with an excursus of the possible other scenarios. So we have seen coupling with gauge fields, production of primordial black holes, but one can also consider scenarios that break space-time symmetries during inflation. So inflation is a nice paradigm, but we don't really know what happened during inflation. Maybe all space-time symmetries were broken, space parameterization, time reparameterization, So people studied this possibility. If you start to break space and time reparameterization, one realizes that during inflation, the graviton, the gravitational wave, the graviton acquires a mass, an effective mass driven by the theory of inflation. In this case, it is interesting because then the spectrum of fluctuations, I will show you in a second, is enhanced at interferometer scales.
I have a question.
Yes.
Brief question. So the equivalence of the breaking of the reparametrization invariance of space-time description, it's equivalent to the fact that graviton acquires a mass.
Yeah.
Okay.
In a
it's
sense,
equivalent.
no, it's not equivalent. What happens is that if you start to break space reparametrization, there is no symmetry that prevents the graviton to acquire a mass. And indeed, when you study these models, you see that calculations at the level of effective field theory, you generate a mass of the graviton. But it was expected because no symmetry prevented it. For general relativity, you don't break space diffeomorphisms, and then graviton does not have a mass. But if you start to consider more complicated theories of gravity, like massive gravity, you start to break space-time diffeomorphisms and graviton acquires a mass. So massive gravity is an example, by gravity are examples, but there can be models of inflation where there are vector fields that break space reparameterization, or some families of scalar tensor theories that are called solid and supersolid inflations. Maybe at the end we can go into details of these models, but the bottom line, believe me, the bottom line is that graviton acquires a mass, and what you can do is to study then the spectrum of the power spectrum of tensor modes produced during inflation. This is the prediction of slow roll inflation. In these models, the spectrum increases going at a larger frequency, and it crosses the sensitivity curves of LISA. It's not detectable by ground base, but it is detectable by space-based experiments. Also, these models produce anisotropic and non-Gaussian stochastic gravitational wave spectra. This is what you see. It's very brief excursus of the theory part. What I wanted to tell you, however, what I wanted to give to you, the feeling is that there are models of inflation that can motivate an amplification of tensor modes of gravitational or primordial gravitational wave spectra at the scale of interferometers. So hopefully, with direct detection, we can then probe the physics of the early universe. But now, let me tell you in concrete a very interesting, in my opinion, a very interesting approach that now theorists can try to develop. Now, what we have is that we know that there are these interferometers that are built or will be built in the future. So what I did in the past years was to try to see whether we can put together theory with future experiments. And I tried to get involved in this space-based interferometer that is called LISA, to see how this space-based interferometer can probe the theoretical models that I developed in the past. So what is LISA? LISA is a very nice idea, is a very nice experiment that will take place hopefully in 2034. So what is this? It is a big triangle. It is actually three. There are three spacecrafts. I hope you can see the small figures. There are three spacecraft in an equilateral triangle that will be sent in space, and they will interchange between them lasers of light. If gravitational waves pass through these between these three spacecrafts, so there will be a distortion that will then be measured by the interferometers. And it will give us hint of possible gravitational waves. So this experiment is huge. Indeed, between the spacecrafts, there will be sites of 2.5 million kilometers long, and it will follow the Earth as it goes around the sun. So you see, it is a very futuristic, but ESA, the European Space Agency, already promised money, and the instrument is under construction. So it has been approved. Now we know what are the details of the instrument that will be launched in 10-15 years. So what I did was to essentially try to see whether we can use these future instruments to probe early and late universe cosmology. So what does LISA measure? I told you it measures light that travel between the spacecrafts. So here the light covers this kind of triangle. So it is possible to define what are called channels that correspond essentially to possible ways for light to go and return back, to go and be reflected by mirrors on these spacecrafts. So starting from the signal, so suppose that we start from a gravitational wave that crosses space-time and passes between the spacecrafts, so along the arms of the interferometers, starting from the gravitational wave, hopefully the primordial gravitational wave from inflation, one measures what is called a sigma, a signal that is called S. So the 2-point function of the primordial spectrum of gravitational waves from inflation is mapped to a 2-point function of a signal that is just time delay of light that goes from one spacecraft to the other. And the proportionality constant depends on the polarization of the gravitational wave, depends on the interferometer channels. It is calculable, and the shape depends on the frequency, depends on the amplitude, the shape is something like this. So it is very nice, at least for me, it was very, I learned a lot how to pass from early universe to really the signal measured by experiments. So why I tell you this? Because then it is interesting to see whether we can try to probe some of the, for example, some of the predictions of these models of inflation, like for example, a particular shape of the spectrum with this kind of interferometers. So let me go, I show to you. So a possibility is then to try to use LISA to probe the profiling frequency of the stochastic gravitational wave background. I told you that different models predict different kind of profiles in frequency. Gauge models of inflation coupled with gauge field produce this kind of power law. Models with primordial black holes, this kind of bumpy behavior. So within the cosmology working group on LISA, we built a code, let us say, an algorithm to probe, to see whether LISA can probe arbitrary shapes of the power spectrum. And we provided an algorithm to show that LISA actually, if the power spectrum has sufficient amplitude, then even, let us say, complicated shapes like bumpy behavior or oscillatory behavior in frequency can be probed with this kind of experiment. So if theoretical cosmologists come out with models of inflation that produce this kind of bumps, we quantified the possibility of LISA to probe this kind of models. Other observable I mentioned at the beginning is chirality. Models of axions that coupled with FF tilde can produce a chiral spectrum, and actually a hint of this possibility has been pointed out by a recent paper by Minami and Komatsu studying CMB polarization. But now let me focus on interferometers. Okay, a chiral spectrum could be probed also with interferometers. So a spectrum of chiral tensor modes from inflation can be probed. It has been shown that can be probed by ground-based interferometers. And within the LISA cosmology working group, we also shown that with some effort, it can also be probed by LISA. One should, however, in this case, for a technical reason, that maybe I can postpone the discussion, one should not focus only on the isotropic part of the stochastic gravitational wave background. One has to look at the anisotropic part, in particular, to study the dipole. But we computed the SNR, the signal-to-noise ratio, and we quantified the possibility to measure the chirality of gravitational waves and parity violation in gravitational waves that come from inflation. So, to summarize the first part of the talk, gravitational waves and cosmology, okay, provides challenge and opportunity. The inflationary paradigm predicts the existence of stochastic gravitational waves from inflation. Its properties depend on the inflationary model. And what I went through rapidly was to try to convince you that some of well-motivated models of inflation might be detectable not only with CMB bimode polarization for what respect the gravitational wave predictions, but maybe also directly detectable with interferometers. Are there any questions before I go to the late universe? So if not, so I will tell you briefly in 10 minutes some possibilities about detecting instead, about using interferometers to probe dark energy, to probe the physics of the late universe. So the idea now is, let's forget about stochastic gravitation or about stochastic background. So stochastic background comes from everywhere. Now let's go and study instead gravitational waves that come from black hole mergers. So we know we measure gravitational waves that come from black hole mergers. What is interesting is that we can learn not only about astrophysics, but also about cosmology. And I will try to tell you why. So the basic question that I want to very briefly tell you is the physics of dark energy. We know that our universe today is accelerating. It might be due to a cosmological constant, but it might also be due to some extra degrees of freedom that make the universe accelerate, or to some modification of gravity. So Javier, in the next talk, will tell you about, I believe, about theory, more about modification of gravity. What I want just to tell you is an example of possible way to test modified gravity with interferometers. And I will focus on what are called standard sirens within the LISA experiment. So what's the idea? The idea is that suppose that we have black hole mergers that are very far from us, then gravitational waves start to travel. They start to travel very far from, and they arrive up to the detectors at the Earth or nearby the Earth. So in their travels, they collect some information about the expansion of the universe or about structure of other fields that are around. Precisely this information can tell us about dark energy. So why I focus on LISA? Because LISA is very good to probe sources that come from very far away. In particular, here is this LISA sensitivity curve, and these are the kind of gravitational waveforms associated with sources, this color one, that correspond to supermassive black holes at very high redshift of order 3. So the events that have been detected with LIGO Virgo are relatively nearby. With LISA, we will be able to probe very, very distant objects. And so gravitational wave travel very distant, very long cosmological distances. And so they collect more information. So in particular, what I want to tell you is the possibility to study this kind of supermassive black holes. What are these supermassive black holes? These are black holes at the center of galaxies. Suppose that galaxies merge, and we know this is a phenomenon that occurs in our universe. The supermassive black holes at their center, they merge, and they produce gravitation, of course, a super loud signal in gravitational waves that LISA is able to detect. So the frequency scale of this signal is precisely within the frequency band that LISA can detect. This is why LISA is very special for studying this phenomenon. In a paper that we wrote within the LISA Cosmology Working Group past year, we precisely studied this kind of phenomena to test modifications of dark energy. As I told you, Javier will tell you a little more about theory, but the idea is the following. So gravitational waves that come from far sources are characterized by what are called gravitational waveforms that correspond essentially to the time or frequency dependence of the plus and cross polarizations of the waves. These waveforms depend on a quantity that is called dl, that is the gravitational wave luminosity distance. It is essentially very roughly speaking, it is the cosmological distance between us and the source of the gravitational wave. This cosmological distance, if we are able to measure it, it tells us a lot about the expansion of the universe, because one can do the calculations and one realizes that this cosmological distance depends on the expansion rate of the universe. So if we are able to measure this quantity, we know about the expansion rate of the universe. In fact, the LIGO-Virgo collaboration already set some constraint on luminosity distance for the events that they measured, and they provided an independent measurement of the Hubble constant using this technique. In our paper, we instead tried to see whether the luminosity distance of gravitational waves can be affected by modified gravity. The answer is yes. There are theoretical models that affect the luminosity distance of gravitational waves that come from supermassive black holes. And we used it in order to provide, let us say, forecasts to see how good LISA will be able to probe models of modified gravity. So we put together astrophysicists and, let us say, modified gravity theorists. So astrophysicists provided a mock catalog of LISA events. So this is these figures at each point correspond to a different example of black hole merger, supermassive black hole merger at different redshifts. So LISA can arrive to very large redshifts. And by doing a statistical analysis, we provided some constraints on modified gravity model, on modified gravity parameters. We showed that some of the modified gravity parameters can be well tested by LISA, while they cannot be tested by other means. So this is an example of plots. So in these plots, the red, okay, Chi0, this Psi0, sorry, is a parameter that is associated with some modified gravity models. So the red part are all the experiments apart from LISA. So you see that the experiments do not constrain Psi0, but if we put all the experiments that are CMB, BAO together with LISA, then this Psi0 can be constrained. We also shown that LISA can constrain the mass of the graviton at a level that is comparable with ground-based experiments. And okay, this plot indeed shown the exclusion plot for the mass of the graviton at LISA frequencies. So with this, so this is the my last slide. So with this, in this second part of the talk, I tried to give to you some example of how gravitational wave experiments, in particular LISA, can be used to probe theories of dark energy. The idea is that theories of dark energy can change the propagation property of gravitational waves, and gravitational wave experiments can detect these small changes in the propagation properties. So this is all what I wanted to say. Y si tienen preguntas, estoy aquí para responder.
Muchas gracias a Gianmassimo, le agradecemos la plática. Entonces, adelante, tenemos tiempo para preguntas.
Can I ask one question?
Yes.
Yeah, nice talk, first of all. Yeah, I wanted to ask, I mean, why the value predicted by LISA for the Hubble constant today is close to the value predicted by Planck? I mean, is there any reason why is it small?
No, okay, so I go to this plot. So the situation is the following. So this is the observation of the single observation of one event of LIGO Virgo that was a very specific event where it is GW170817 of LIGO Virgo, not LISA, where they measure both the gravitational wave and the electromagnetic counterpart of a neutron star picture. Okay, so it was not a black hole, it was. So you see the error. So by, let us say, it is reassuring that there's the central value of the Hubble constant that they measure is between what has been measured by the CMB, by Planck collaboration, that is little h0 over the 0.68. It is between that and between what is measured by supernova. Okay, so the error bar is huge. However, it is not conclusive. However, in the future, if other events will be measured with electromagnetic counterparts, or if there will be sufficient statistics of what are called dark silence, or many black hole mergers, and we are able with statistical methods to study to understand from where they are by studying catalog of galaxies, etc. So they will very optimistically we will arrive to a 5% error, let us say, on the Hubble parameter. The fact that the central value is around 0.7 is what everyone was hoping and expecting. What is very important is that these measurements are completely free of systematics. So they only depend on the theory of gravity. The fact that the central value was around the one of Planck and of supernova is, it means that everything is consistent. All theories are consistent. To go to LISA, so let me just finish. To go to LISA, there will be again independent measurements that come from very high redshift, in this case, from this kind of supermassive black hole mergings. So in this case, this will be a standard science that where we can measure both the gravitational wave, and there are astrophysical models that tell us that during the merging, due to this kind of plasma or due all the stars that are around, there will also be sort of lumps. There will be a sort of electromagnetic counterparts. So we'll both measure the gravitational wave and the electromagnetic counterpart. What is the error bar on H0? The estimates are around 5–10%. So we will have, it will not be as good as supernova, but it will be a lot better because with much less systematics. So we don't need to know the details of supernova physics. It is much cleaner within GR. If we modify GR, there would be additional effects. we tested possible modifications of GR. Javier will tell us a little more in the next talk. Good thing, okay, now what people are starting to study is how to break the degeneracies between modified gravity and GR in perturbed universes. There are a lot of physics to develop. I just told you the tip of the iceberg, but yeah, there is a lot to do.
Okay, thanks. And actually, I have another
Yes.
question or requesting to clarify. Sorry, can you please comment again on the reason behind the enhancement of the scalar, the amplitude of the scalar power spectrum during inflation?
Okay. I talk about the enhancement of tensor spectrum, or do you want the one of primordial black hole?
The scalar, that one, this one, yeah.
Okay. So primordial black holes. So forget completely for a second about gravitational waves. So suppose that what we want is to have a model that produces black holes from inflation. Okay. What you need in order to do so is to enhance the spectrum of scalar modes, not tensor modes, bigger to a certain threshold. Because if you enhance the spectrum of scalar modes at a values larger than a certain threshold, so there are sufficient scalar fluctuations, sufficient, depends on the gauge, but a sufficient amount of density fluctuations to produce a black hole. Okay, so to produce a black hole, one has to overcome a certain threshold of density fluctuations. You can produce it by astrophysics, so collapsing objects, so you need to have very dense environments, or you can have dense environments from inflation. Because if inflation produces a very strong, at certain scales, a very dense spectrum of scalar fluctuations, then you can produce these primordial black holes. Okay? Doing so, however, by this kind of second order effects, these very dense scalar fluctuations, they also enhance the spectrum of tensor fluctuations. So this kind of density fluctuations produced by the scalar fluctuation from inflation also enhance the spectrum. So you have, let us say, for free, you have both primordial black holes and a spectrum of tensor of gravitational waves that you can test with gravitational wave experiments.
Okay, thank you.
No problem.
Tenemos tiempo para una última pregunta. Julio Alberto Méndez parece que tiene una.
No, no te escuchamos.
No, ¿verdad?
Can you hear me now?
Sí.
Sí.
All right, thanks. So my question is more generic from the cosmological part of the talk, and this is about the effective mass of the graviton that it acquires.
Yes.
Is there some sort of cosmological screening mechanism, such as the Weinstein mechanism, so that in late time we do not observe an effective mass?
No, yeah, here is, yeah, it is, okay. Weinstein here doesn't, we don't have any spherical source. We don't have any source. Here everything is very isotropic, so we don't expect any kind of nonlinear Weinstein mechanism. So here the idea is super, let us say, phenomenological. So the idea is that we want to explore the possibility to give an effective mass to the graviton during inflation. One can do it with vector modes that break space reparameterization, scalar modes, or even consider models of by gravity motivated by DRGT or other things, but everything at the super effective level, quadratic action. We don't consider any nonlinear effect here. So we didn't, people so far did never worry about possible nonlinear effects that come from possible, let us say, consistent completion of this kind of models to avoid ghosts. No one worries about that. Above all, because the motivation was, first of all, to try to explore the possibility that with these kind of approaches, one amplifies the spectrum at laser scales. So it was a very, let us say, so far a phenomenological approach. So people didn't then consider much effects on nonlinearities, non-Gaussianities, etc. They have been a little studied, but not so much.
Okay, thank you very much.
Muy bien. Yo quiero despedir nada más a Gianmassimo con una última pregunta muy genérica para quizá todos nuestros estudiantes que nos están viendo que comienzan con esto y hablando un poquito sobre el tema de las posadas. ¿Podrías decirnos lo más brevemente que puedas qué debemos entender por gravedad cuántica y por qué es importante estudiarla?
Gravedad cuántica, esto es muy personal, digamos, es muy personal. Bueno, a mí me fascina, pero para mí, súper honestamente, se tiene que hacer mucho esfuerzo ahora para entender si podemos utilizar las nuevas posibilidades que nos ofrecen las ondas gravitacionales para ver si con experimentos podemos testar la teoría que más te gusta. Ahora, yo soy extremadamente pragmático. Si me dices, creo en cuerdas, creo en quantum gravity, que llegan de otros lados, para mí todo está bien. Si es consistente, lo que quiero entender es si ahora mi interés es ver si con ondas gravitacionales que salen de black hole mergings o si con ondas gravitacionales que vienen de early universe, si podemos testar lo que me dices, las teorías tu teoría preferida de gravedad cuántica. Pero ahora tenemos una muy grande oportunidad que no teníamos hace 5 o 10 años. Y en mi opinión, ahora se tiene realmente que disfrutar lo más posible. Ahora, como saben, el tema de ondas gravitacionales es gigante en todo el mundo. Y para mí es muy interesante lanzarnos los más teóricos para ver si podemos testar nuestras teorías con ondas gravitacionales. Personalmente yo lo hice con mis modelos de inflación y con los modelos sobre los que trabajé en gravedad modificada. Quantum gravity me gustaría muchísimo, pero todavía no hay mucho, pero se tendría que hacer. Por ejemplo, todos los nuevos déjame terminar un ejemplo. Los nuevos resultados sobre black hole evaporation, ahora parece que la gente entiende mucho mejor black hole evaporation y cómo resolver las paradojas de Hawking. Hay varios wormholes y todo. Perfecto, vamos a ver cómo testarlo. También en el futuro, en 50 años, no importa, pero vamos a ver si existen, si se puede al menos construir experimentos, pensar experimentos para testar estas nuevas ideas que están saliendo.
Muchísimas
Esta
gracias.
es mi opinión.
Sí, muchas gracias. Te agradecemos, te agradecemos la plática y muchas gracias por haber participado aquí.
Gracias a ustedes.
Gracias.
Ahora.
Bueno, los dejo ahora con Miguel Sabido. Miguel, ¿andas por ahí?
Sí, bueno, continuamos. ¿Sí me escuchan?
Sí, adelante.
Bueno, pues de nuevo agradecer a Gianmassimo y ahora seguimos con la siguiente charla. Un poco como comentó Oscar, las ideas era tanto los invitados como algunos de nuestros egresados participaran aquí en este evento. Y entonces ahora continuaríamos con Javier Fernando Chagoya, con su charla. Déjame, aquí tenía el título. algunas pruebas no tan clásicas de la teoría de gravedad. Entonces, nomás quería así rápidamente mencionar un poco de Javier. Bienvenido, Javier. Pues él estudió aquí en la Universidad de Guanajuato. Tuve la oportunidad de trabajar con él durante su doctorado. Y después hizo un postdoctorado en la Universidad de Swansea. Regresó a México como cátedra CONACYT y ya tiene una plaza como profesor de tiempo completo en la Universidad Autónoma de Zacatecas. Se ha convertido en un experto en gravedad modificada y pues más que nada darle la bienvenida y pues darle control aquí de la sesión.